So in this video, we're going to practice using the ideal gas law. What does it actually let us calculate? How do we use it? And so in one example, let's start just with a balloon. So we have a balloon that has an initial volume of, let's say, 1.5 liter. The temperature, so temperature initial, was room temp 293 Kelvin. The pressure outside today is just about 1 atmosphere, so 1.0 atmospheres. What I want to know, how many moles were in that balloon? So it was a party balloon. I blew it up. I breathed into it a few times until it was 1.5 liters in size. I'm kind of curious, just how many moles of gas did I breathe into that balloon? Well, ideal gas law lets us solve that. It says I have a volume. It must have an outward force equal to the inward force. So if there's 1 atmosphere outside, I must be 1 atmosphere inside. And so I can figure out the pressure of my balloon. It's 293 Kelvin, so those particles were bouncing, so fast. We can factor that in. If I only had 1 particle, well, it would only hit the walls a little. I must not have too big a volume. So how many particles would it require to push this out to be 1.5 liters? That's what we can solve. I have pressure volume equals N RT, and my goal is to find N. To do it, I need to get it on its own. You need to rearrange the equation. So if I divide RT on both sides, they'll cancel on the right, and I'll just have moles on its own, and I'll have moved RT to the other side. So pressure volume over RT will equal my moles. Well, my pressure was 1 atmosphere, so 1.0 atmosphere. Our volume was 1.5 liters. R value, well, for that, I need to think about my units. I have atmospheres, I have liters, I have kelvins, I have moles. R is 0.0821 if we're using those units, atmospheres, liters, mole, and Kelvin. So 0.0821 atmospheres, liters, mole, Kelvin. And my temperature, 293 Kelvin. So take a second, tell me, figure out the moles, and then let's check it. So I have 0.062356 mole, and realistically we had 2 sig figs, so 0.062 mole. Now, if you accidentally found 5353 moles, then what you did is you accidentally multiplied by 293 instead of dividing by 293. Depending on your calculator and how you use parentheses, in my calculator I had 1 times 1.5 divided by 0.0821 divided by 293. If you're not using parentheses, you need to enter it this way. A lot of times I see folks accidentally say, oh, the bottom is 0.0821 times 293. But if you don't have the whole bottom part in parentheses, then it accidentally multiplies everything by 293 instead of putting it on the bottom. So I'm going to do that one here so you can know if you accidentally got 5,353 moles that you need to adjust how you're entering into your calculator. If you got the 0.062 moles, then spot on. This is how many moles is actually in the balloon. And a 1.5 liter balloon is probably about 3, maybe 4 breaths normally for folks, unless you got really big breaths. So we can use the ideal gas law to solve for the moles, or for any of the variables. There's 4 variables. There's the pressure, the volume, N, R, and T. R is a constant, but the other 4, as long as we know 3 of them, we can solve for the 4th. So let's go back. I had volume initial was 1.5 liters. Temp initial was 293 Kelvin. Pressure initial was 1 atmosphere. And we solved our moles. We said, oh yeah, it's 0.062 mole. I leave the balloon out for a little while. Well, the volume has decreased. Maybe it had a little hole. Maybe the pressure changed. We're not certain. But my volume is down to 0.90 liters. Temperature today, as time went on, so we'll call it volume final, temp final, it got a little colder. It's 285 Kelvin now. Pressure, well, it didn't really change. We're near sea level, so it still looks about 1 atmosphere. So I want to think about the moles. Did my volume decrease because my temperature went down? Or did I also lose some gas? So the question here is, what is my final moles? Did I lose any gas? Or is all of the shrinking of the balloon simply because of the temperature? Try that. Give that a calculation. Come on back and see what we get. So for me, and I know I shorthand wrote 1 atmosphere, but we'd had it 1.0 last time. Just so we don't lose our sig figs, let's make that 1.0 atmospheres. But 1 times 0.9 divided by 0.0821 divided by 285 returns us 0.03846 moles. What we find is, no, our moles are actually a lot lower. Our temperature only changed by, 8 degrees. 8 out of nearly 300 is less than 3%. So the temperature change was only about 3%. We should only see about a 3% change in our volume, but we lost more than a third of the volume. So some of our change came from the fact that there was a leak in the balloon. We actually have less moles now than we did originally. And so to 2 sig figs again, this would be 0.038. And so we lost some of our gas. And this, we were able to use the ideal gas law to determine that. Yeah, our moles after some amount of time was less. Our balloon must not have as much gas in it. We don't just solve the moles. You can also solve the volume you expect something to be. If you have a large cylinder, if you have a large gas tank, and it has an enormous amount of gas in it, well, these are actually dangerous. They have to be chained up, because if they tip over, they can fill rooms and cause incredible danger. If you tip a nitrogen tank over and it suddenly fills the room with nitrogen, there's no oxygen left. People can asphyxiate and pass out and die because there's no oxygen to breathe in the room. If I have one of these tanks, they're generally about 57 liters at 12 atmospheres at room temp. And so if I have one of these tanks, well, I want to, and they can get way over 12 atmospheres. This is actually a lower pressure one. But I want to figure out here is if this expands to full size at 1 atmosphere. So basically it busts open because there's more force on the inside than outside. It suddenly expands and spreads out. I want to know is what's the new volume. Well, in our case, I've got a volume, a temp, and a pressure. I can solve the initial moles. I can say, hey, how many moles were in that original tank? Those moles are going to spread out into a new volume at a different temp, a different pressure. Because we're going to have some final over here. There's going to be a volume final that we want to know. The pressure must match the outside, and we're saying the outside was 1 atmosphere. So that'll be our pressure final. Temperature, as long as you give it a little time, it's just going to be room temp again. So we're going to be 293 Kelvin. And that's one thing about the ideal gas law. It assumes that you give things time to reach what we call equilibrium, to balance out. If you ever used a compressed air can, it is cold when it first comes out, but it warms up very quickly as it meets all the other warm gas in the room. So giving it time to expand a little bit or giving it time to warm up will be the same temp. And in theory, our moles should be the same. The moles that escape to fill the room should be those same moles. So if I can solve those moles that are in the tank, I will know the moles to put in so I can solve for the volume. So I have to find those moles. Well, I've got a pressure, 12 atmospheres, a volume, 57 liters. I've got an R value, 0.0821 atmospheres, liters, mole Kelvin, and I've got a 293 Kelvin. So I can solve those moles. I get 28.4345 moles with 2 sig figs, but we'll keep it all so that we can use it in our next calculation. 28.4345 with 2 sig figs. That's how many moles must have spread out. So as this tank tipped over and burst open and the gas spread to fill the room, what I want to know is what is the volume it spread out into. So take a second. Now we know the moles. Find me that final volume. How much space does it take up? All right, well, if you're back, I want to find volume this time. Well, PV equals nRT. I'm not solving for N, I'm solving for volume. I need to get volume on its own, which means I need to move pressure off of the left side. So I can divide by pressure on both sides. It'll cancel on the left. My volume will equal my moles, my R, my T over my pressure. Moles 28.4345. My R, still using atmospheres, so 0.0821 atmosphere liter mole Kelvin. My temperature, 293 Kelvin. And my pressure, 1 atmosphere. So what is my volume final when that tank tips over and bursts open and spreads all the gas out? 684 liters with 2 sig figs. So about 680 liters. And so I wrote atmospheres with just 1 again. But you can assume at sea level that it was a little more accurately 1.0. So just so we have enough good sig figs, let's go back and correct that. So I've got about 680 liters of volume, which actually isn't all that much. This is actually a pretty small tank. 12 atmospheres is pretty low compared to what these can fill a room with. Generally, you'll have something that's up around 120 atmospheres, and so this will be 6,800, which is almost 7 cubic meters. As that spreads out in a room, it might take up, a solid hallway in size. And as it does so, if it spreads a little further, it just decreases the oxygen content. You don't actually have to push all the oxygen out, but if you drop a room's oxygen to, 3/4 or half of what it was, humans will pass out. And so it's very dangerous when these tanks tip over. So there's a few examples of running the ideal gas law. Critical components to remember: you have to rearrange the ideal gas law so that you get whichever variable you want to know on its own. So if you say want temperature, then I need to move N and R off of the side they start on, so they cancel out, you divide by it, and you have to do the same to both sides. So effectively I just move N and R over to the left side. But that gives me a version of the ideal gas law that says pressure and volume divided by moles and R will equal my temperature. And we can do this for any of the variables. We just have to rearrange so that we have the one we're solving for on its own. So as long as you know what it is you're trying to solve for, we can use the ideal gas law to find it, as long as we know 3 of the other variables.